Assalamualaikum warahmatullahi wabarakatuh to Madam Siti Hajar. For this video assignment, we will be presenting Chapter 2, which is Vector Calculus. What we will talk about in this chapter are the del operator gradient of a scalar field, divergent, curl of vector field, Laplacian, flux and divergence theorem, and last but not least, the line integral and Stokes theorem.
Today, I will briefly explain two important concepts in a vector calculus: the gradient of a scalar field and the gradient of a vector field. First, the gradient. When we apply the del operator to a scalar field, we get a vector field called the gradient. This gradient shows the direction in which the scalar field increases the most and how fast it increases. A good way to imagine this like standing on a hill. The scalar field is the height of the hill and the gradient point in the step face uphill direction. The stepper is the larger gradient. This is useful in many physical applications like temperature or pressure field. Next, the divergence of a vector field. Divergence tells us how much the field is going out or coming in at a point. For the example, you all can imagine placing a tiny balloon in the vector field. If it's a positive, the field is going out like a balloon inflating. If negative, the balloon going in like a balloon deflecting. If nothing changes, it is a zero divergence. This helps us know if the point acts like a source, a sink, or stay neutral.
Now, I'll briefly explain the curl of a vector field. Curl measures how much a field rotates around a point. Essentially, it tells us the local spinning or rotational behavior of a vector field, like fluid, flow, or magnetic field. You can see the orange diagram on the top right. The arrows show rotation around the center, representing a vector field with curl. Mathematically, the curl is expressed using the cross product of the del operator with a vector field, shown here in three coordinate system: Cartesian, cylindrical, and also spherical. Each form helps us apply curl depending on the symmetry of the problem. For example, cylindrical for pipes and spherical for planetary field. In short, the curl helps us understand the rotational nature of vector fields, which is the key in physics and engineering like analyzing fluid dynamics or electromagnetism.
The Laplacian is a second-order differential operator that combines the effect of the divergence of a gradient and is commonly used in electricity and magnetism to describe how a scalar field behaves in a space. In Cartesian coordinate, it is expressed as the first formula shown in the slide. However, in cylindrical and spherical coordinate, the Laplacian takes different form to suit problem with specific symmetries. For example, in cylindrical coordinate, it is involved derivative with respect to rho, phi, and z, while in spherical coordinate, it is include derivative in r, theta, and phi. To make it easier to understand, we can use the analogy of heating a metal plate, where V represents temperature. If a point is hotter than it is surrounding, the Laplacian is negative. If cooler, it is positive. And if the same, the Laplacian is zero. This concept helps us visualize how quantities with electric potential and temperature spread in space, and whether a point acts as a source, sink, or in equilibrium, as also illustrated in the 3D plot on the slide.
Now, let's talk about flux and the divergence theorem. Flux simply means the amount of vector field like air, fluid, or force that passes through a surface. The formula shown here calculates this flow using a surface integral. The divergence theorem connects the total flux through a closed surface to the divergence of the field inside the volume. You can see the equation here. It says the total outward flux is equal to the volume integral of the divergence inside. To make it easier to understand, imagine a balloon. The flux is like the total air escaping through the balloon surface, while divergence tells us how much air is being produced or lost inside the balloon. So, basically, the divergence theorem helps us simplify surface calculations by looking at the inside of the volume instead.
Assalamualaikum and hi. In this part of the video, I will explain two important concepts in vector calculus, the line integral and Stokes theorem. These tools help us understand how a vector field behaves along a path and how it's related to the rotation of the field over a surface. First, let's talk about the line integral of a vector field. Imagine you are walking along a path through a vector field, like wind or force. The line integral tells you how much of that field pushes you along your path. Mathematically, it's written as the line integral of vector A dot dl along the path L, where A is the vector field, L is the path, and dl is a small piece of that path. The dot product means we are only interested in the part of the field that is tangent to the direction we move. This is commonly used to compute work done by a force along a curve. Now, what if you want to relate this path to a surface? That's where Stokes' theorem comes in. It connects the circulation of a vector field around a closed curve to the curl of the field over the surface it encloses. It's written as the line integral of vector A dot dl around the closed path L is equal to the surface integral of the curl of A dot ds over the surface S. This means instead of computing the line integral directly, we can calculate the curl of A, which tells us how much the field is rotating, and integrate it over the surface S bounded by the curve L. This is powerful because it can simplify calculation and gives deep insight into the field's behavior. In summary, the line integral measures the flow along a curve, and Stokes' theorem tells us how that flow is related to the field's rotation over a surface. These are fundamental tools that help bridge local and global behavior in vector fields.